Welcome back to my YouTube channel. And there is something that is now something that is triggering a lot of confusion in the world. We have AI taking up most of the stuff, and then there is something in the background called quantum computing. Most of you are still duped in AI, in artificial intelligence, in ChatGPT, in Gemini, Llama, but there is a big guy in the background, and that's called quantum computing. And today, I want to bring you what is quantum computing, what is it about, and what is its limitations and capabilities. Probably this is one of the fields that most people have not read through, because even me myself, I'm doing a master's in computer science. I've not taken my time to learn about quantum computing. I only saw one girl who is lady who is into quantum computing. She has made she made her first research paper in quantum computing. I was supposed to present on the same panel because me I'm into machine translation, but unfortunately I was not ready to present. But this lady has presented so far like two times in major conferences talking about quantum computing, and that's the future of computing, because now we have algorithms, we have encryption, and quantum computing will make all that encryption look like crap. This is something that is now come wake up. Basically now people who studied in the long times don't know about quantum computing. Actually, some does not go to class from I actually had quantum computing. It's like this semester when I had somebody who I think was in recent advances in quantum computing, and that was a course unit. And this is my first time to hear about a course in quantum computing. And now today I said, okay, let's go into quantum computing together. These notes were prepared by Joseph Stelmach and me as his student. I decided to give a brief lecture about quantum computing. We are discovering quantum computing together, and we get to know what is it all about and what is taking place in the quantum computing world. So let's start. We start. So introduction, we're going to see by the end of this, we're going to have introduction and history. We are going to see data representation, we're going to see operations on data, we're going to see Shell's algorithm, we're going to see conclusions and open questions. And this week I'm going to be delivering a series of lessons on quantum computing, because people are already into quantum cryptography, which is encrypting data in the quantum era. We're going to see what is quantum computing. Some of you have heard about quantum mechanics, and very few people study about quantum mechanics apart from those who do mechanical engineering. They are the ones who touch quantum mechanics. The rest don't touch on quantum mechanics. Quantum, we're going to see what is quantum. You are dealing on the atomic level. Now, what is a quantum computer? So from day, a quantum computer is a machine that performs calculations based on the laws of quantum mechanics, which is the behavior of particles at the subatomic level. This is so ridiculous, because the computer that we know just performs calculations based on zeros and ones. That's digital. It's either on or off. You find you have numbers written in terms of zeros and ones, but this quantum computer is dealing on the behavior of particles at the subatomic level. Okay, now quantum computing. Let's see the most people that started this ridiculous stuff, this crazy stuff. You know, most of these inventions have been out of being crazy. Crazy guys come up and write crazy stuffs, and the crazy stuffs come up to be the norm of the day. Like the times people started coining something like artificial intelligence. I remember sometime this guy, when the law Okay. Relativity. When Albert Einstein made relativity and then gave it to these other guys and then they turned it upside down. Okay, let's see this man. Feynman. I think I can safely say that nobody understands quantum mechanics. This was Feynman, 1982. Feynman proposed the idea of creating machines based on the laws of quantum mechanics instead of the laws of classical physics. We have quantum physics, then we have classical physics. Classical physics is the basic physics, laws of Newton's laws of motion, something like that. But then now we have quantum mechanics. So we go. 1985, David Deutsch developed the quantum Turing machine, showing that quantum circuits are universal. The year 1994, Peter Scull came up with a quantum algorithm to factor very large numbers in polynomial time. Phew, polynomial time, like a number to power something, power 1, power 2, power 3, power 4, and upwards, up to power 1 million. That is polynomial. And then we have Love Grover develops a quantum search algorithm with O, the square root of n complexity, 1997. What is these guys have in their brain? Now, we move on to data representation. We are going to see, now we have seen the history. There's some history that is missing. I was going to show you about, I will show you later. Okay. So now we see data representation. We see that qubits. A bit of data is represented by a single atom that is in one of the two states noted by 0 and 1. A single bit of this form is known as qubit, and a physical implementation of a qubit could use the two energy levels of an atom. An excited state representing 1 and a ground state representing 0. You get it. So we have here, we have a nucleus. This is an atom, of course. We have a nucleus, we have an electron, these are the shells. Then we have the excited state, then we have the ground state. So this is the electron. Now, light pulse of frequency lambda for interval t. As it goes through, this is state 0. Now, once the electron is here at the ground level on the first shell, once it gets this light pulse of frequency lambda at interval t, it will gain sufficient energy and then will jump from the ground state to the excited state. And in the next state, in the state of 1, it has gone to the excited state. Okay. Now, superposition. A single qubit can be forced into a superposition of two states denoted by the addition of the state vectors. So it is 0 plus 1. Two states denoted by 0 and 1. So where alpha 1 and alpha 2 are complex numbers and alpha 1 squared plus alpha 2 squared is equal to 1. Okay, this is the magnitude. Magnitude of alpha 1 squared plus alpha 2 squared is a 1. So a qubit in superposition is in both of the states 1 and 0 at the same time. This is ridiculous because the normal computer, normal data representation, you either have 1 or a 0. Now this qubit can have 1 and 0 at the same time. Anyway, this is quantum. So a light pulse of frequency lambda for time interval t divided by 2. This is ground state. Then it goes to the excited state. Consider a 3-bit qubit register. An equal weighted superposition of all possible states would be denoted by. This is ridiculous stuff. Okay, in general, how do you retrieve the data? In general, an n-qubit register can represent the number 0 through 2 to the power n minus 1 simultaneously. Sound too good to be true? It is. If we attempt to retrieve the values represented in a superposition, the superposition randomly collapses to represent just one of the original values. And then now, in our equation, alpha 1 represents the probability of the superposition collapsing to 0, and then the alphas are called probability amplitudes. In a balanced superposition, alpha is equal to 1 over root 2, where n is the number of qubits. So entanglement, relationships among the data. You know what it means by to be entangled. Now entanglement is the ability of quantum systems to exhibit correlations between states within a superposition. So that's the definition of entanglement in quantum computing. Imagine two qubits, each in the state 0 plus 1, a superposition of the 0 and 1. We can entangle the two qubits such that the measurement of one qubit is always correlated to the measurement of the other qubit. Oh, sorry. Now we go to the operations on data. Operations on qubits, reversible logic. Due to the nature of quantum physics, the destruction of information in a gate will cause heat to be evolved, which can destroy the superposition of qubits. Let's look at the AND gate, A, B, where we get a C, and B is a C. Now, for an AND gate, if the n state is a 0, then the output is a 0. If it will be on when both the states, the input states, are on, 1, 1. In these three cases, information is being destroyed. That is, the first, the third, the second, and the third. It's only the fourth where the information is not destroyed. So this type of gate cannot be used. We must use quantum gates. My God. So now, those who know AND gates, you don't know anything. It's very unfortunate to tell you that you don't know anything. You don't know anything. So we must use quantum gates. So my brother, we're going back to quantum gates. Now what is a quantum gate? Quantum gates are similar to classical gates, but they do not have a degenerate output. Their original input state can be derived from their output state uniquely. They must be reversible. This means that a deterministic computation can be performed on a quantum computer if it is reversible. Likely, it has been shown that any deterministic computation can be made reversible. That is by Charles Bennett, 1973. What? So actually, you find that this quantum computing is not something that is coming out of the blue. It is something that has been existing, but it has taken shape now. Because, so, quantum gates, we're looking at Hadamard. Simplest gate involves one qubit and is called a Hadamard. is called the Hadamard. So, also known as a square root of a NOT gate, it is used to put qubits into superposition. So guys who did classical gates, who did AND, NOR, NOT, XOR, NOR, OR, you actually don't know anything here. But anyway, you have the knowledge, but now you need to upgrade it, just like I'm doing. Yeah, because I studied gates in my bachelor's, and we had discrete mathematics, we had digital logic, we had computer architecture. Then I came to do it at my diploma aircraft maintenance engineering. I had to do fundamentals of digital logic. Yeah, that's again studied about gates. So I have some knowledge about gates. Now I come to quantum computing, and we have a quantum gate which is called a Hadamard. And this gate is a square root of a NOT gate. It is used to put qubits into superposition. We have the state of 0, that is the ground state. Then we have the Hadamard. Then it goes to, it is in between. It exists with the 0 and the 1 at the same time. This is ridiculous. Then we add another Hadamard, and then we get the excited state. Two Hadamard gates used in succession can be used as a NOT gate. Now, controlled NOT. A gate which operates on 2 qubits is called a controlled gate. A controlled NOT gate, which is called a CN gate. If the bit on the control line is 1, invert the bit on the target line. The gate, if the bit on the control line, which is B, invert the bit on the target line. If this bit is 1, then on the target, invert it. Now let's see how it works. We have A, we have B. These are the target. This B is a control. Now both are zeros, so meaning the output is 0. We have 0 on the target. The control is 1. So if the control is 1, then the bit on the target is inverted. When we invert 0, we get a 1. And that means same thing here. We have a bit here, 1. We have the target 1. The control is a 0, meaning the control will remain 0, but the target will remain 1. That is the invert of the target, the output. Now we have 1, both are 1, 1, meaning we invert. Get this clearly. When we have a 1 on the control, the target must be inverted. Just like here, we had a 1 here, we invert the output on the target. Here we had a 1, we inverted. The target remains with its own bit. The target affects the control maintains its bit. It only affects the target. The CN gate has a similar behavior to the OR gate with some extra information to make it reversible. So it is not actually different that Okay, the Cn is similar to the XOR gate. If you, but this Cn gate has extra information to make it reversible. Let's go on. Example operation, multiplication by 2. We can build a reversible logic circuit to calculate multiplication by 2 using Cn gates. Cn, we said it is a controlled NOT gate. It's arranged in the following manner. We have the carry bit, then we have the ones bit, 0, 0, 0, 1. So, if the bit on the control is 1, then you invert. That's why here we have this inverted, something like that. Controlled NOT gate. Controlled NOT. Quantum computing is ridiculous. Controlled NOT. What's this? If the bits on the if and only if. This one means if and only if. If you have if like this is if and only if. The bits on the both of the control lines is 1, then the target is inverted. Meaning we have the control 1, then we have the control 2. And they are all affecting the targets. So if both are 1, that's on state when the target is inverted. We can see it here. 1, 1, then the target is inverted to 1, from 0 to 1. 1, 1, the target is inverted from 1 to 0. The rest, the target maintains its bit. Universal quantum computer. The CCN has been shown to be a universal reversible logic gate, as it can be used as an AND gate, as a NAND gate. So when our target input is 1, our target output is a result of a NAND of B and C. So if we check through, we shall find that it behaves like a NAND gate. 1, 1, NAND result of B and C. This is 1, 1. This is the 1, so it becomes 0. This is 1, 1, and it is 1. Shor's algorithm. Shor's algorithm shows that a quantum computer is capable of factoring very large numbers in polynomial time. The algorithm is dependent on modular arithmetic, quantum parallelism, and then quantum Fourier transforms. Those who have done Fourier transforms, those mathematicians know what Fourier transforms are, and physicists. Okay, all who have done engineering course know what Fourier transform is, and know what the Fourier series are. So, an important result from number theory. F of A is equaling to x power A modulo n is a periodic function. Choose n is equal to 15 and x equals 17, and we get the following. 7 to the power 0 mod 15 is equal to 1. 7 to the power 1 mod 15 equal to 7. 7 squared mod 15 equals 4. 7 3 mod 15 equals 13. 7 power 4 mod 15 equals 1. Now, this thing reminds me of last semester we had a course about applied mathematics, and that's where everything we're doing was modulo something. We got sick about what is modulo, and you now come to understand that mathematics for computer scientists, modulo is something that is very important. You must understand what modulo means, because here mod is like the remainder. So when they used to teach us about mod 5 in mathematics, this was something that was preparing us for the future to come. We are here. 7 power 4 mod 15 is a 1, meaning it is congruent to that. Shor's algorithm in depth analysis to factor an odd integer n. Let's choose 15. Choose an integer q such that n squared is less than q and less than 2n squared. Let's pick 256. Choose a random integer x such that the greatest common denominator of x and n is 1. Let's pick 7. Yeah, the GCD of 15 and 256. Create two quantum registers. These registers must also be entangled so that the collapse of the input register corresponds to the collapse of the output register. Oh, I'm tired. Oh, let's go to conclusion. In 2001, a 7-qubit machine was built and programmed to run Shor's algorithm to successfully factor 15. What algorithm will be discovered next? Can quantum computers solve NP-complete problems in polynomial time? So we meet next time, and that's all the lecture was, and I'm bringing more lessons about quantum computing